Okay, good evening, everybody, and welcome to another session of organic chemistry. In today's session, we are going to start with chapter 2, which is concerned with a series of foundational topics and concepts. Foundational topics and concepts. Which will lay, of course, the foundation for your understanding of organic chemistry as we move along during the course of this semester. So just as in the case of chapter 1, these topics and concepts are very, very important. But before we start today's lecture on chapter 2, let me make a couple of quick announcements. Our own work assignment is due on Sunday, September 8th at 11 p.m. And also, I do have your quiz graded already, so I will give them back to you at the end of this lecture. So make sure you stop me close to about 5 minutes to the end of class, so I could give this back to you. Also, before we start on chapter 2, what I would like to do, I would like to give you a few more information on chapter 1, so we can close the chapter on the content of chapter 1. So let us call this chapter 1 revisited. Remember, we spent most of our time on chapter 1 taking a look at the ground state electronic configuration of atoms. For example, if we take a look at the ground state electronic configuration of carbon again, we draw the graphical energy profile for the different electronic shells. We know that the carbon atom has how many atomic, what is the atomic number for carbon? I mean, what is it? 6. And that means carbon has how many electrons? 6 electrons. Very good. So you have the different atomic orbitals. So we have one S orbital with 2 electrons. And then you have 2s orbital also with 2 electrons. Then you have 2p orbitals. This is 2s, and this is 2p. We have 1 electron here, and 1 electron here. The last atom, the p orbital of carbon atom does not have any electron. Now, if you now take a look at this, you say this here, this is the valence shell for carbon atom, and in that valence shell we say we have a total of 4 electrons. Now, we also told you about the octet rule. In order for carbon to obey the octet rule, how many electrons does it need in its valence shell? It needs 4 more, right? It needs a total of 8. That is why we call it octet rule. So it needs 4 more electrons. That means that carbon, we want to form covalent bond. I mean, we want to form 4 covalent bonds. So therefore, we say carbon has a valence or 4. In other words, carbon wants to form 4 bonds in order to share 4 electrons that will give it an octet of electron in its outermost shell, which is the valence shell. So we could also therefore say carbon is tetravalent. Therefore we could say carbon is tetravalent. Tetravalent means that carbon needs 4 bonds. Now, so this is the case for carbon. Now, if we take a look also at some of the elements or atoms that we are going to be using with regard to organic chemistry, if we take a look at oxygen, let's take a look at oxygen. We draw the graphical electronic energy shell. What is the atomic number of oxygen? 8. So therefore oxygen has how many electrons? 8 electrons. Very good. So we have 2 electrons in the 1s orbital, another 2 electrons in the 2s orbital, and then the 2p orbital, the 3 of them, 1, 2, and 3. You have here, you have here, you have here, electrons here. So how many electrons have we used so far? How many? 7. So therefore we place the 8 right here. So now if you take a look at this again, take a look at the valence shell of oxygen. How many electrons does it have in the valence shell? How many? 6. So you say the valence electrons for oxygen is 6. Therefore, how many electrons does it need in order to attain the octet? 2. It needs 2 more, which means that oxygen will want to form 2 covalent bonds, right? So therefore, we say oxygen has a valence of 2. Notice what we say here, valence. Valence simply means the maximum combining power for any atom. Write that here. Valence equals to the maximum covalent bond for any atom. That is what valence is. So therefore, we say oxygen is divalent. These are the terminology we are going to be using as we go along. So the reason I do want to take some time to explain this, so when I say divalent, tetravalent, you know exactly what that means. Okay, so therefore we say oxygen is divalent. Okay, oxygen needs 2 bonds in order to attain the octet. Now we do the same thing for nitrogen. Okay, what is the valence? How many? What is the atomic number for nitrogen?
7.
What is it? 7. Good. So we need 6 electrons, right? 1s, 2s is 2 electrons. Then you have the p orbitals. Okay, so we have 1 here. Fill this out first. Okay, so now we have how many more to go? How many more to go? Electrons to go? It's all gone, right? Is it 2 more? For nitrogen. What's the atomic number? 7. So we have 7, right? Okay. Now, so therefore, we look at this again. This is your valence shell with the valence shell with 5 valence electrons. So how many electrons does nitrogen need in order to obey the octet rule? 3. So therefore, what will be the valency of nitrogen? 3. So nitrogen will be trivalent. Okay? So therefore, nitrogen has a valence of 3 in any stable molecule. So therefore, we say nitrogen is a trivalent. Now we could do the same thing for chloride. Okay? Notice that for each one of these atoms that we've just done, all of the atoms below them, well, let me go ahead and do fluoride anyway. All of the atoms in the same group will have the same valence. In other words, if you look at oxygen, below oxygen, what do you have below oxygen in that group? Sulfur. That means sulfur will also be divalent. Okay? If you look at nitrogen, what is below nitrogen? What is it? Phosphorus. That means phosphorus will also be trivalent, at least in many cases. The same thing applies to the case of sulfur. Okay, in many compounds of sulfur, it will be divalent. Okay. Now let us take a look at fluorine. What is the atomic number of fluorine? What is it? 9, right? You say 9? Okay, good. So we have to distribute 9 electrons in the atomic orbital, in the various electronic shell of fluorine. So you have the 1s with 2 electrons, the 2s with 2 electrons. Now you have this here, the p's. Okay, so we say we have a total of 9. So 1 goes here, 1 goes here, 1 goes here. So far we've used 7, right? So 2 more to go. Therefore this will be filled. Therefore this will be filled. Okay, now we have, in the case of fluorine and those other atoms below it, how many electrons does it need to form an octet? 1. So therefore, what is the valence of fluorine? 1. Okay, in other words, fluorine is monovalent. Okay, so fluorine has a valence of 1. Therefore, it is monovalent. Okay. Okay, finally, before we move on, let's just look at hydrogen. In the case of hydrogen, what is the atomic number of hydrogen? What is it? See? What is it? 1, so it has only 1 electron. Very good. Okay, so for here, hydrogen, 1s, you only have to worry about this right here. So now it has one electron in the only electronic atomic orbital that it has. Now, how many electrons does hydrogen need in order to have a completely filled electronic shell? 1. Because for the first electronic shell, all you need is 2 electrons. Okay, so therefore, what this means, hydrogen will always be monovalent. All it needs is to form 1 covalent bond. Okay, so hydrogen has a valence of 1. Therefore, it is monovalent. Okay? These are very important. Let me now give you a summary of what we just done so far. Very important, because when you are going to begin to solve problems, you are going to need all of this information. Okay, summary of what we just summary of valence, at least for those atoms that are important to the organic chemists in this class. Hydrogen, 1, right? We know carbon is 4. Oxygen is what? What is the valence of oxygen? 2. Nitrogen, what is it? 3. Okay, and fluorine is what? 1. And keep in mind, all of those other atoms below them in that same group will also have the same valence, at least for the most part. Okay? Okay, now, another set of information I want to share with you. Remember, we did a lot about hybridization last week. We only talked about the hybridization for carbon atoms. But those hybridization, these processes that we went through last week with carbon, we could also have the same for oxygen and nitrogen. We are not going to do that today, but I'll simply just give you the outcome. Say, for example, if you have this here, supposing we have this molecule. This molecule, this is the molecule, this here. This is methanol. This is an alcohol. Okay, now if you take a look at this, does carbon have an octet of electrons? Yes. 1, 2, 3, 4, 5, 6, 7, 8. Keep in mind, each one of these bonds is 2 electrons. About oxygen, does oxygen have an octet of electrons? Based on what we've drawn here. No. How many electrons surrounds, at least is present in the valence shell of oxygen, the way it is drawn right here? 4. So how many more does it need? 4. Therefore, you have to place 4 electrons here, 2 pairs of electrons, 1 pair here, 1 pair here, okay, in order to give the oxygen the octet of electrons. Now, supposing, therefore, I ask you, what is the hybridization of this oxygen? Okay, I'll tell you right now, the hybridization is sp3. This is an sp3 oxygen. Why do we say that? When this here, this non-bonding electron we have here, we refer to them as lone pair of electrons. Okay, so this is a lone pair of electrons, this is another lone pair of electrons. Or sometimes we refer to them as non-bonding electron pairs. Non-bonding electron pair. Now, each non-bonding electron pair, when it comes to hybridization, you have to assume that the non-bonding electron pair is actually a bond. Okay? Keep that in mind. When it comes to hybridization, anytime you see a lone pair of electron or non-bonding pair of electron, you should consider that as a bond. In other words, keep in mind that this is in an orbital like this. This is in an orbital like this. And therefore, if you consider each pair as a bond, then you will say that oxygen has how many bonds when it comes to hybridization? 4. And that is why we say this is an sp3 oxygen. Okay? Yes. To do what? On the atom? Yes, that is why I say with oxygen and also nitrogen when we get there. Anytime you see a lone pair of electrons, consider that a bond for the purpose of hybridization. Okay. Yes. Just at least for your case, a lot other atoms will be in that same category. But in your case, let us simply focus on oxygen and nitrogen at this point. Okay. Now, so we say this is an sp3 oxygen. Now, supposing I have this. Supposing I have this. Supposing I have that. Okay. What I've drawn here is a line bond structure for this molecule, or what we refer to as calculate structure. Does carbon have an octet of electron around it? Yes or no? Yes. So each carbon has an octet of electron. Okay, make it easy for you to see. Supposing, okay, the way this is drawn here, I then ask you, does oxygen have an octet of electron? The way it is drawn, no. So what does it need? Need 2 more pairs, right? So therefore, you have to place this right here. So this molecule also have oxygen with 2 lone pairs of electrons. Now, supposing I now ask you, what is the hybridization of this oxygen? What is it? Say that loud. sp2. Very good. Excellent. That is sp2. Because you consider this here, bonded to an atom, and then this is another atom here. So in other words, you have this oxygen, essentially, think of it as being bonded to 3 atoms. Okay? Because each one of the lone pair of electrons you consider as an atom. So therefore, this is an sp2 oxygen. So therefore, this is an sp2 oxygen. Okay. Now, what I want to do now, before I go to chapter 2, let us do a few problems in chapter 1. Because the more problems you do in organic chemistry, the more you understand organic chemistry. And I will also advise that you guys should begin to do a lot of problems, and that is why I assigned the problem set in R, and also you need to do some problems in the back of your book. It will help you. Okay. Supposing I give you this molecule here, C3H4, based on what we know now. Based on what we know now, I give you a molecule. I said, this is the molecular formula for a stable molecule. And I want you to give me the calculate structure or the line bond structure, line bond or calculate, the same thing, from this here. What are we going to do? Now, notice what we are in organic chemistry. What do? We give you a bunch of information. And then when it comes to solving problems, we require that you think critically. In other words, we force you to think critically. This series of information we just give you is not just knowing them, but you got to know how to apply them. So you have to be able to think very critically. Okay? So let us test your critical thinking knowledge here. So what do we do? Okay, the first thing, of course, we do, we say, well, we have 3 carbon atoms here, right? So we join them. Okay, we join 3 carbon atoms. Fine. We have 4 carbon atoms. Right? You could attach them to anywhere. Where do you want to attach them? Help me out, sir. Yeah, go ahead. 2 on, very good. 2 on each end. Very good. That is one possibility. 2 on each end. Okay. So now we've exhausted all of the atoms that we have, right? Now, what do we do now? We need to obey the octet rule, and we need to obey the valence rule. Anytime you have any problem to solve, writing a structure, keep in mind, you have to obey the valence rule. All those valence that I gave you, you got to obey the valence rule and the octet rule. You know that if you are dealing with a stable molecule. Okay, so let us take a look. We know we don't have to worry about hydrogen. Hydrogen has a valence of 1, so it's happy. And we don't need to worry about octet for hydrogen because it only has 1 electronic, the 1s electronic energy shell. The maximum in it is 2, so it's happy. About this carbon atom, does he obey the valence? No. Valence is 4, right? Does he obey octet? No, right? Right now it has 6. So how many more does he need? 2. Okay, let us look at this carbon. About this carbon, it doesn't obey the octet nor the valence. Okay, so we say maybe there's a double bond here. That is why we say now you have to begin to think critically. Okay. So is this carbon happy? Is it happy? Valence is obeyed, right? Octet is also obeyed. Okay, very good. Is this carbon happy? No, because the valence is, okay, valence is 4. Also doesn't obey the octet. So this is where you now begin to use those various concepts. About this carbon? Does it? So therefore we say this carbon needs 2 electrons, this one needs 2, so we place. Is that an acceptable molecule? Yes. Yes. Because it obeys octet and valence. So that is good. Okay. Is there any other possibility for this? Let us see. Supposing we have this. Supposing we have that. Supposing you simply started with this, you place hydrogen here. You could do that too, right? You could do that, right? There's nothing stopping you from doing that. Okay? This carbon is happy, right? But this carbon is not happy. So we have 2 more hydrogens to go. Because the formula is this here. This is the formula we have to use. Okay, so we place hydrogen here. Okay, can you do anything with this? Can you do anything with this structural framework? I call this, at this point, structural framework. Can you do anything with it? No, you cannot. Because this carbon is happy, it doesn't need any more bond, but this carbon needs something. And this carbon needs something. So we cannot use this structural framework. We have to begin to see how you have to think critically. Okay, let me give you another problem. Any question on this? Okay. Why can't we lone pair of where? On where? Okay. Okay, very good. So you say, why can't we place lone pair here, right? Right? And lone pair here, right? Okay, very good. Okay, so right now this is only 2, right? So you need to put, you want to put 3 lone pairs here, right? Is that what you're saying? Okay, let's go along with that. Supposing we do this. Very good question, by the way. Okay? Supposing you do that. So now you say you have 8, right? But let us take a look at this. This is chapter 2 that you got me to chapter 2. I tell you what, you cannot do this because I don't want. When we get to chapter 2, I will show you why you cannot do this. Okay, because it gets what we call formal charges. Then you have to begin to place formal charges and do something else with this molecule. That will not work. Okay, because if you look at this, we say that carbon must have 4 bonds. At this point, it only has 1 bond. So the valence is not obeying any kind of valence. The same thing on this here. If you place electron here, we say carbon must be tetravalent. This is only trivalent, so we cannot do that. You follow what I'm saying here? So you see, I have to follow the valence rule and the octet rule. Okay. In this case, the valence rule, you are not obeying the valence rule, even though you place all of these electrons here. But like I said before, when we get to chapter 2, we need to see some other aspects of this. So you cannot do that because you are not obeying the valence rule when you write this. Okay, you follow that? Okay. So this will not work. Okay. Now, supposing I have this. C3H8 oxygen. Okay, I want you to use this formula here to write a line bond structure for this molecule or a calculate structure for this molecule. Okay, so what do we want to do? What do you want to do? Write carbon out first, right? Good. 3 carbon. Okay, and then you want to place oxygen somewhere, right? Okay, that's fine. Now we have 8 electrons to go, so we begin to place the electrons. 8 hydrogens to go, so we begin to place the hydrogen. Place here, 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 here. How many hydrogens have we used? 5. Okay. Here, here. How many more to go? Okay. Keep in mind, you must obey the valence rule or the octet rule. Okay. Or both of them. You got to obey both of them. If the molecule has to be stable. Okay. So is this carbon happy? Valence wise and octet? Yes. About this carbon? Yes. About this carbon? Yes. About this oxygen? Yes. No? Okay. Valence is okay? Right? Valence is okay, therefore. Exactly. Place the known pair of electron right here. Okay? Very good. Now, the last one before we go to chapter 2. Supposing I give you this structure here. And I simply tell you, this is the structural frame or just structural model of a stable molecule. Structural frame or structural model simply means that this is not the complete structure, and I want you to complete the structure. Okay, give me the complete structure for this molecule. All of the atoms are there already. Okay, so what do? Let's start with oxygen. What do we need to do with the oxygen? What is wrong with this oxygen here? Valence is not obeyed, right? We need to obey the valence and the octet. About this carbon here, valence is also not obeyed, or octet. Both of them are okay. So what do we need to do? A double bond, exactly. So you place a double bond right here, right? Then what do we now need to do with the oxygen? Does oxygen have lone pair of electrons? How many? 2 pairs. Okay. Okay. So now oxygen is obeying the octet rule, is also obeying the valence rule. Okay. Let us now go to this carbon here. About this carbon. Valence, is it happy? No. Octet? No. About this carbon. Valence? No. Octet? Okay, therefore, you could place a double bond between them, right? Okay? Okay? So each one of the carbon is now happy. Each one of them is now tetravalent. And each one also has an octet of electron in this valence shell. I mean, valence electronic orbitals. Okay. Huh? You what?
Why did you not just add a hydrogen?
You cannot. We already told you this is all of the atoms that are present in the molecule.
Okay.
This is almost like giving you the molecular formula.
Okay.
You follow this? You cannot just make it up.
Right.
Okay. Okay. Now, about this carbon. It's happy, right? Okay. About this carbon. No. About this carbon. So what do we need to do? Exactly. Excellent. I see you guys are getting the idea. Now about this carbon. Okay. What does it need? A triple bond, because you have to obey the valence. So it needs a triple bond. Okay, if you do a triple bond with nitrogen, is nitrogen happy? Valence-wise? Valence-wise, valence. About octet? No. What do we need to do? Exactly. Okay, so this is when I say you have to think critically, that's what we mean. If we have given you all of the information, we've given you valence, we give you octet, now it's now left to you to actually use them in problems. And this is the kind of thing you are going to get. Nobody's going to ask you, what is the valence of oxygen? That's ridiculous. Nobody's going to ask you, what is the octet rule? No. But we will test it by giving you this kind of problems to test your understanding. Okay, before I go to chapter 2, any question on chapter 1? Okay, chapter 1 is gone forever. Oh, okay. Okay, so now let us go to, how much time do we have? I know, we always have plenty of time. Oh wow, a lot of time. We got close to about 40 minutes left. That's it. Okay. Okay. Okay, as I promised earlier, I said we were going to start with chapter 2. And just as in the case of chapter 1, I told you a lot of concepts in chapter 2, just as in the case of chapter 1. And all of these concepts, you should consider them as foundational concepts or foundational topics, because this will lay the foundation for your understanding of organic chemistry in subsequent chapters. We are going to discuss polar covalent bonds, electronegativity, dipole moments, formal charges, resonance. All of these are big topics. Okay? And then we'll discuss acid-base reactions as they relate to organic molecules. Okay. On this slide, of course, I have a list of what I consider to be learning outcome objectives. These are a list of learning outcomes that you should use to guide your studying of content of this chapter. For example, you should be able to identify the direction of bond polarity. If I give you a molecule, you should say, oh yes, this is the direction of bond polarity. You should be able to determine the formal charge on different atoms in a given molecule. So all of this in here, use this as a guide to study for the content of this chapter. If you recall, last week, how many types of bonding did we tell you according to the valence bond theory? How many types of bonding did we tell you that we have in organic chemistry? 2. We told you that we have covalent bond and we have ionic bond, right? Those are the 2 we gave you. Indeed, those are the 2 extremes of bonding in organic chemistry. There is a third type of bonding which is somewhere between those 2. And we refer to that as polar covalent bond. Think of it this way. Remember, in each one of the bonding, say for example, we say we have this. We have carbon here bonded to oxygen. What we are assuming here, we are making an assumption that carbon and oxygen will be sharing those 2 electrons because you have 2 electrons between them. We are making an assumption that carbon and oxygen will be sharing those 2 electrons equally. That is not always the case. That is not always the case. And therefore, we have what we call polar covalent bond. Polar simply means uneven distribution of electrons. Okay? Polar in organic chemistry means uneven distribution of electrons. uneven distribution of bonding electrons in a covalent bond. And why do we have uneven distribution of electrons? If we go to the next slide, we have this table here. All of these atoms here, we have what we call electronegativity values for each one of these atoms. And electronegativity is the ability of each one of those atoms to pull bonding electron to itself. Electronegativity is the ability of each atom to pull bonding electrons to itself. It's almost as though, what's her name again? Kayla, okay. Between you and I, we are pulling a rope, right? The chances are I'm stronger than you. So I'll put the rope more to myself. That is all it is. Those two electrons, one atom is pulling more to itself. That's what it is. And the way you know that is to have this table of electronegativity values. You don't have to memorize this table. So whenever you need it, we would let you have the table. If you look at this, the most electronegative atom is fluorine with a value of 4. Then you have oxygen, 3.5. Nitrogen, 3. Carbon, 2.5. In other words, nitrogen is more electronegative than carbon. Oxygen more electronegative than carbon. The same thing with fluorine. Of course, you could see here, hydrogen is less electronegative than carbon. So any bond between hydrogen and carbon, carbon will be pulling more of the electron to itself. Okay? So this table of electronegativity values, therefore, we use that to guide us in describing whether a bond is polar or not. Okay? We say, is this bond polar or not? In other words, does it have an even distribution of electrons? So this table of electronegativity will come in very handy whenever you have to taking a quiz or an exam. But it's better to just know it right away. Okay, but if you need it, we'll let you have the table. Let's give you a couple of examples. Look at this molecule here. That's the molecule of methanol. That's the molecule of methanol. I could simply just write it this way. It would be better than that. Molecule of methanol. If you look at this here, the carbon-oxygen bond will be a polar bond. It will be a polar covalent bond because this oxygen here, oxygen has electronegativity value of, what is oxygen? 3.5, right? Okay. And carbon is 2.5. So you could see right here. Between this carbon and this oxygen, the difference in electronegativity value is 1. So anytime you have a difference in electronegativity value of 5 or greater, or, I'm sorry, 0.5 or greater, then you say that bond is a polar covalent bond. Okay? 0.5 or greater to give you a polar covalent bond. Okay. Supposing I have this here. Supposing I have a bond between hydrogen and hydrogen, what kind of bond would that be? What would that be? A non-polar, yes, it's a covalent bond. That's a classic case of a covalent bond because you have equal sharing of electrons. So we therefore say, just like who said that over there, say non-polar. That would be a non-polar bond. Okay? So that is a classic case of a polar bond. I'm sorry, a covalent bond. Most bonds in organic chemistry are close to being polar covalent. Okay. Now, take a look at this molecule here. We call methyl lithium. Methyl lithium. The bond between carbon and lithium. We look at the electronegativity value for carbon is 2.5, lithium is 1.0. The difference between them is 1.5. Anytime you have the difference in electronegativity value getting close to 2, that bond will be almost like ionic. Any electronegativity difference of close to 2 would be an ionic bond. Okay? So the chances are this could be an ionic bond. The bond between this carbon and this lithium. It's a borderline case of polar covalent and ionic. Okay. Now, as you can see here, in order to indicate that this is a polar covalent bond, what do we do? We say that this here, this oxygen has a partial negative charge. We use the Greek symbol. Sigma to indicate that this has a partial negative charge, and because it is pulling electron away from this carbon, we say the carbon has a partial positive charge. And therefore we say the direction of polarity, the direction of pull of electron, we use this arrow here to indicate the direction. Okay? We use a cross arrow to show that the direction of pull is toward the oxygen, just as you can see here. Just as you can see here. In other words, in this case, the direction of the pull is towards carbon, because carbon is more electronegative than lithium. Okay. Now, we could now take this even further. Just as we can measure the polarity of individual bonds, we could also measure the polarity of a complete molecule. Take a look at this here. We could measure the polarity of a complete molecule. And that measurement essentially is an aggregate of all the polarity of the individual bonds. Okay? And we refer to that as a dipole moment. That aggregate of measurement of bond polarity, we refer to it as dipole moment. So we could actually measure this. We'll ask you, yes? Yes, it is like an extreme case of polar covalent getting close to ionic. Mm-hmm. That's in the case of methyl lithium. Is that right? Okay. So, we could actually determine the net polarity, which we refer to as dipole moment, for a given molecule. So we say, does this molecule have a dipole moment? In other words, is it a polar molecule? That is important because it could determine whether the molecule will be soluble in water or soluble in organic solvent. So a polar molecule will be soluble in water, a non-polar molecule will be soluble in organic solvent. So we could actually use this to determine some of the chemistry that we will be doing in the future, in terms of what solvent do you need to use for this reaction. So anyway, take a look at all these molecules here. We have water molecule. We could measure the dipole moment. The dipole moment is given in mu, and the unit of measurement is in what we call the bar. That is just the unit of measurement. So we say water has a dipole moment of 1.85. In other words, water is a polar molecule. It does make sense because we say polarity is essentially uneven distribution of electrons. If you look at water molecule here, you see this lone pair of electrons on this side of the molecule. So that part has a lot more electrons than the part that has the hydrogen atom. Okay, if you take a look at the methanol molecule, the same thing. You see here, the direction of polarity is here, just as it is shown here. Look at this ammonia molecule right here. Ammonia molecule with a lone pair of electrons. Also, it is a polar molecule, and the direction of polarity is right here. Now, typically, any molecule, on the other hand, molecules, let me write this for you, symmetrical molecules generally have zero dipole moment. In other words, the dipole moment will be zero. Net dipole is zero. Now, what do we mean by that? Now, on the other hand, if you have non-symmetrical molecules, on the other hand, will typically also have some kind of dipole moment. Let's see, I think. Okay. Take a look at these molecules here. Carbon dioxide has a zero dipole moment. Why? Because it is symmetrical. Look at methane. Methane is also symmetrical, zero dipole moment. Ethane, symmetrical. Benzene, also symmetrical. So how do we normally ask you this kind of question? We'll give you a bunch of molecules. Say which one of these molecules has a dipole moment. For example, if I do this, supposing I add this, do you expect that molecule to have a dipole moment? Yes or no? Yes. Nobody's going to ask you what is the dipole moment, because that is a measurement that you have to do with an instrument. We don't expect you to know the dipole moment unless we give it to you. That is an empirical data. But we expect you to know, to recognize a molecule that is a polar molecule that also has a dipole moment. So this molecule will have a dipole moment. And what is the direction of the dipole? Towards the chlorine, right here. So this has a partial negative and partial positive on carbon. Okay. Supposing I give you this. Do you expect that molecule to have a dipole moment? Do you expect that molecule to have a dipole moment? No. That's a symmetric molecule. Everything will cancel out. Keep in mind, when we do the dipole moment measurement, it's an aggregate of all the individual dipole moments for the individual bonds. So this will cancel out. So this will be zero. Okay, supposing you have this. Okay, do you expect that to have a dipole moment? Yes, yes. The direction of dipole will be towards this direction right here. Okay, because you have bromine, and bromine, they are more electronegative than carbon. Okay, so yes. Yeah, go ahead.
Yes, bromine was on the other side of the sea, like when the first entry, then it wouldn't, right? And then it kind of
Excellent question. Good. Okay, the question is, supposing I wrote bromine, if it was instead of here, let me take this off. If I take this off, right, I place hydrogen there. Is that what you say? Okay. The question is, supposing we have this, and the bromine is here, right? Okay. Very good question. Okay. Very good. I want you to think of this. Think of this as hydrogen. What do I have? Think of this as hydrogen, right? The reason why you asked that question, which I said this is an excellent question, let me have this trained on myself. It's because of the way we are looking at it. Think of this as the bromine. Because of the tetrahedron nature of this carbon. Okay? Okay. If I look at here, right? I'm sorry. Bromine, right? Look at the way it is. Look. They are both pointing to that side. If you look here, right? If I look here, they are still both pointing to that side. Even though I could write it, depending on the way I write it on the whiteboard, it will be looking as if they are coming towards me. But the molecule is still the same. It's just the way I wrote it. Okay, but if you look at this here, the direction of the bromine, both of them are still going here. So this will still be a polar molecule. Would have a dipole moment because both of the hydrogen will be here. No matter how you look at this molecule, the difference is the way you look at it is different, but the molecule remains the same. I could look at it this way. It doesn't change the molecule. Okay? Ms. Howard could decide to look here. It doesn't change the molecule. So anyway, so it's a good question though. Sometimes when we get to stereochemistry, that becomes very important because the way you write the molecule it depends on the way you see it. Okay. Anyway, so anyway, we've gone from the polar bond to a polar molecule. In the case of polar molecule, we could measure the polarity by what we call the dipole moment. Okay, and I also told you that for symmetrical molecule, the dipole moment will be 0 because the individual polarity will cancel out. Okay, now, what time do we have? Got too much in there. Oh, yes. We're almost there. Huh? No, you said 5 minutes, yes. I got 20 more minutes, believe it or not. Okay. Now, another concept I would like to introduce to you is what we call formal charge. This is also a very important concept. Sometimes, remember we have been telling you, in order to determine whether a molecule is acceptable in terms of stable molecule or not, you got to consider the valence and the octet. Sometimes a molecule may, the atoms in a given molecule may obey the octet rule, but may not obey the valence rule. In that case, you have to indicate a formal charge. Okay? It may obey the octet rule, but it may not obey the valence rule. Okay? So, formal charge, therefore, is that charge that you place on an atom in a stable molecule or in any given molecule. To reflect the fact that the valence electrons, the electrons that surround the atoms, is different from the valence electrons of that atom in its natural state. Okay, what do I mean by that? Let us look at this molecule here. This is nitro. Nitromethane molecule. Take a look at this here. This nitrogen here, does it obey the octet rule? Does it? It does. It does. Does it obey the valence rule? It doesn't. So in that case, even though it obeys the octet rule, if it does not obey the valence rule, then you must place a charge on that. That's what I was trying to tell somebody who asked me the question much earlier, that get to formal charge. Now you must place a formal charge on that atom. And how do you get the formal charge? This is the formula I wanted to use. This is different from the formula in your book. I believe this is much easier to use. The formal charge of an atom in any given molecule is the valence electrons in the free state. So in the case of this nitrogen, therefore, what is the valence electron of nitrogen? How many valence electrons does nitrogen have in its free state? If you look at the periodic table. Amen? To do what?
You said the nitrogen doesn't obey the valence rule, right?
Yes, because nitrogen, the valence of nitrogen is 3. But this nitrogen here has 4 bonds. So it is violating the valence rule, right? It has 4 bonds. Okay? So because of that, we must place a formal charge on that nitrogen. And so therefore we say the formal charge is number of valence electrons in its natural state. You guys say it is 5, right? So in this case we have 5. And number of valence electrons that actually belong to the atom in the given molecule. Now if you take a look at this molecule here, how many valence electrons actually belong to it? Not sharing. How many? 4. Okay, 1, 2, 3, 4. Actually belong to it, not sharing. We're not talking of sharing now. So therefore, that becomes 5 minus 4 equals to plus 1. So therefore, you place a plus 1 charge on that nitrogen. Because it is only 1, you don't need to write the 1. Just place plus. Well, if you just say plus, we know that is plus 1. Okay, that's how you arrive at the formal charge. And that happens whenever you have a molecule in which atoms within that molecule, they obey the octet rule, but they do not obey the valence rule. Yes? Okay. You see some example of that. About this, in this molecule here, you see the reverse right here. In this molecule here, look at sulfur. Does sulfur obey the octet rule here? Does it? Yes. Does it obey the valence rule?
No.
No. The valence for sulfur is supposed to be 2 under oxygen. But it has 3. So therefore, what do? We do the same thing. What's the valence electron for sulfur is 6, right? 6 minus, how many electrons actually belong to it here? 5. 1, 2, 3, 4, 5. So we place a plus charge on sulfur. Okay, now the question you asked me about the reverse. This is about oxygen. About oxygen. Okay, does it obey the octet rule? Yes. It has 8 electrons surrounding it. Does it obey the valence rule? What is the valence of oxygen? 2. It only has 1. So therefore, we must place a charge on oxygen. And so if we use this formula here, becomes the valence electron for oxygen is 6 in its natural state, 6. And how many electrons actually belong to it? 7. 7. That becomes minus 1. So therefore, we place a negative charge on oxygen. So that is how you arrive at the valence. You guys look tired. Should I let you guys go at this point, or one more? One more topic. One more. We almost finished. We almost finished. I know. Yeah, okay, let me talk about resonance. Then we'll go. Resonance. Okay, I'll tell you what, 7:22. I think you guys are looking tired. Okay, I'll let you go for today. When we come back, we are going to continue on chapter 2. And on Tuesday, there will be a short quiz on today's lecture alone. There will be a short quiz on Tuesday based on today's lecture alone. Yes. No, it will be, when I post it, I will say chapter 2, lecture 1. Yes. Yeah, I will. Okay, so I will give you back your quiz, and also I will, before I leave tonight, if the internet works well, I will post this in Blackboard tonight, the lecture tonight, and also in my YouTube website. Okay? Keep in mind, on Tuesday, there will be a short quiz, 10 minutes quiz, based on today's lecture alone. Okay, so enjoy your weekend. I will give you back your quizzes.